Okay, we continue with studying how the possible outcomes of hypothesis testing should be evaluated. So imagine we perform a test and there can be two outcomes. We calculate a p-value and then compare that with alpha, and we end up either rejecting the null hypothesis or we fail to reject the null hypothesis. But what could be the reality? Once we reject, that doesn't mean that null hypothesis is totally false. It also doesn't mean it's correct. Perhaps it being correct is less likely, but still there is some chance. So we can describe these different situations in this table. So our decision in the test with the sample we collect, and when we compare the data we've collected with the null hypothesis, we might have failed to reject or we might have rejected. And if we rejected and the null hypothesis was really false, take the vaccine example. If we said there is, in the vaccine example, the null hypothesis was there's no effect of the vaccine. And if we reject that, and if indeed the vaccine is effective, so the null hypothesis false, we've come to a correct conclusion. We could also have failed to reject and the null hypothesis, and the null hypothesis might in reality also have been true. So perhaps there is really no effect of the vaccine and we fail to reject, so we're still okay. But it's also possible that, for instance, the null hypothesis is false, there is an effect of the vaccine, but we fail to reject. And that's called a type 2 error. And it can also be that the null hypothesis is true, so the vaccine has no effect, but we rejected the null hypothesis. Vaccine has no effect, but we rejected. We said the vaccine has an effect, may have an effect, and that's called the type 1 error. So rejecting a true null hypothesis is called a type 1 error. Failing to reject a false null hypothesis is called the type 2 error. Okay, so sorry, yeah, that's repeating the same thing. Also, a common term used to describe a type 1 error outcome is the false positive. It's called a positive because when we reject, we usually say there is an effect, right? When null hypothesis is true, when there's no effect, and we reject, and we say there's an effect, that's called the false positive. And when the null hypothesis is false, so there is actually an effect, but we fail to reject, that's called the false negative. And an easy way to imagine these outcomes is considering a COVID test result. A false positive, the null hypothesis would be no COVID, right? Null hypothesis would be no COVID. And if the patient has no COVID, but the test is positive, that would be a false positive. And if the patient has COVID, but the test says negative, that would be a false negative. In the case of in the pandemic situation, of course, which one is more dangerous? Because the false negatives are dangerous. So when people were talking about tests and how accurate they are, it wasn't really always clear in the media whether they were talking about false negatives or false positives. And tests can have very different rates of false positives and false negatives. And of course, what would be most important would be the false negatives in the case of a COVID test, because that's how you would, a test with a high rate of false negatives would allow the virus to continue to spread. The test with a lot of false positives, the side effect would be you would be locking down many people for no reason, but that might be less problematic in the long term. Yeah, so type 1 and type 2 errors, how frequent they occur. They're both errors, of course, but of different types and different consequences. As you see, false positives and false negatives can be harmful in different ways, and they can increase or decrease depending on different conditions. Yeah, so one important condition is the alpha itself, the alpha we choose. That's the threshold we choose a priori before the experiment. Is chosen to decide on whether to reject or not to reject. If you have to make a decision about whether there's a statistically significant, whether there's a real effect or not, what threshold you use. So this, as we said, is the maximum amount of false positives you are willing to tolerate. And it's a subjective value. Yeah, it will depend on the condition. So if we choose, we can, in different circumstances, we can be more, let's say, liberal, and we can be more relaxed and choose a high alpha. So then it would be easy to reject the null hypothesis, but that would also mean we would be reporting many false positives, right? We'd be inclined to report a signal, even if something that can happen randomly 10% of the time, you would say there's an effect. So that's a statistically liberal or relaxed approach. The just opposite would be if you chose a low alpha, then this would mean it would be difficult to reject a null hypothesis. Okay, difficult to reject. Okay, I should in fact emphasize this part. So you wouldn't easily be rejecting a null hypothesis given the data. And that's called, this is an important term, that's called being statistically conservative. Okay, not politically, statistically conservative means not rejecting a null hypothesis, not claiming things easily. Okay, only when there is a very low chance of something being random, you say there's an effect. You don't make statements easily. That's statistically conservative. So yeah, please also learn this term. It's commonly used. Yeah, so if we choose an alpha that is low, we would be statistically conservative. If we choose an alpha that's high, we would be more liberal or relaxed. And that will determine, of course, also the false positives we have in, we can produce in our test, which alpha we choose. So for instance, in the example of the toads, this was the null distribution, as you remember. So this was the observed value we got, and we calculate the p-value as follows, right? We summed up this area, and also we summed up this area. Okay, so the alpha threshold of point, let me see, yeah, 0.05, it would correspond to here. And so we would be rejecting the null hypothesis. So alpha 0.05 corresponding to this point means any observation beyond beyond this would be considered too extreme and would be reported as something potentially real. But we could also have chosen an alpha of 0.1, for instance. Sorry, 0.01, 1%. And then we would not have rejected, of course, also here, we would not have rejected the null hypothesis. Okay, depending on which alpha we choose, we would have or would not have rejected the null hypothesis. If we are more conservative, we might say just 14 out of 18 is not a strong enough signal. We would want to see more extreme results to be able to believe that there is handedness in frogs. Okay, for different reasons, based on other types of information, we might be inclined more to believe or less to believe. We might be inclined more to accept and follow this claim or less to accept. Yeah, so alpha 0.1, we said it makes it easier to reject. 0.01, for instance, makes it more difficult to reject. Which one is better? It will depend on the situation. So for instance, if you're trying to decide on whether to use a vaccine, a preventive vaccine, and which is known to have no side effects, then perhaps you can be relaxed about false positives, right? The vaccine might not be effective, but if it has possibility of being preventive, then why not use it? And eventually it might turn out to be not effective, but might be okay. But then if the issue is something that will have a lot of cost, let's say health costs, you want to, based on some data, you have to decide if somebody has to start a serious chemotherapy with strong side effects. Then to really decide that this is necessary, you might want to have serious evidence. You don't want to have false positives because it might harm the person. And so you might prefer to be more conservative. Yeah. So depending on the field, in fact, in physics, for instance, in experimental physics, as well as I know, many times they use more strict p-values, like alpha 1 in 1,000 than alpha 5 in 100, as we do in biology, because they perhaps can control their experimental setups, collect more data more efficiently. And in biology, it might 0.05 might also change. I mean, it's something people came up with historically 100 years ago, but it's not like a golden number. There's just a trade-off between how much false positives you would be willing to tolerate versus how much signal you want to catch in the data. And of course, if there are too many false positives, it also means there's less reproducibility, etc. Yeah, or when claiming which alpha would you choose to claim that a student has cheated? Well, yeah, would depend on your philosophy, I guess. Yeah, how would alpha affect the type 1 error and the type 2 error? Okay, think about this for a second. And I guess it would be easy to see that the lower the alpha, if you choose the lower alpha like this, you would have fewer false positives, so lower type 1 error. Type 1 error is false positives, right? So lower the alpha, lower type 1 error, but then you will also have higher type 2 error. You would be missing to reject some false null hypotheses. Let's just remember what type 2 error was. This situation when null hypothesis is false, there is actually an effect, but you fail to reject. That's a type 2 error, right? and when alpha is low, that is some outcome that can happen. Yeah, so the trade-off in biology, as we said, it's a compromise. We choose 0.05. Our data is usually noisy, so to catch a signal with limited sample size, usually we can't be too strict, but that also means we're producing many false positives. Yeah, and again, this might change in the future. Now we'll be talking about related concept. We talked about type 1 and type 2 errors, and now we'll learn about power. And power is the probability of rejecting a false null hypothesis. It's just the opposite of type 2 error probability. So probability of rejecting a false null hypothesis is the inverse of the probability, or say it's 1 minus the probability of not rejecting a false null hypothesis, which is type 2 error. High power means low type 2 error, low false negative rate, and power depends on two things. So it depends on the studied effect, on the effect that is being studied, and we can also describe that as the difference between reality and the null hypothesis. Okay, if the null hypothesis and reality are exactly same, the null hypothesis is not false anyway. Reality and null hypothesis might be very different, then the effect is very large and power will be high. If null hypothesis is false, but it's pretty close to reality, then the effect is small. Power also depends on the standard error. Okay, and standard error itself depends on two things. So this is a repetition of what I was just saying. The power of the test depends on the study of effects and standard error. The effect is the difference between reality and null hypothesis is usually something, I mean, not usually, it's something we don't know when we're performing hypothesis testing. We don't know the reality, we just have coined the null hypothesis, we don't know the reality. And then it depends on the standard error, and the standard error itself has two components, as you remember. It depends on the standard deviation of the population, which we estimate from the standard deviation of the sample. And that is something, a characteristic of the population that we can't change anyway. But it also depends on sample size. Standard error is, as you remember, you should definitely remember this formula. The standard error is sigma divided by square root of n. And then if we don't know sigma, many times we don't know it, we just use S, the sample standard deviation, divided by square root n. So this is the standard error. This is a formula that you should know by heart. And the larger the sample size, the lower will be the standard error. And this is what we can control, okay? If we increase the sample size, the standard error will decrease and the power will increase. Okay, so collecting more, and this should be very intuitive. You don't have to remember the formula for this. I mean, remember the formula anyway, but if we have larger sample size, we have more information, and we will have more power to identify a signal, to identify any difference between reality and null hypothesis, okay? So we can identify any pattern much more easily if we have more data, more information. And here is a small simulation. Let me see. Yeah. So it starts with a description of the null hypothesis in blue, and red describes reality. And what you see, so in the null hypothesis, there's no effect, it's at 0. And the reality might be just like the null hypothesis, or it might be very different from the null hypothesis. This distance is the effect. And as the reality moves away from the null hypothesis, power increases. As you see, if reality is close to the null hypothesis, power decreases. And another effect is, of course, the standard. If the standard error is small, then these distributions are more narrow. So it becomes, again, easier to distinguish between the null hypothesis and the reality. And thus we can have more power of the test. Okay, so here power is 100% because all the samples we will be collecting from reality, their means will be beyond the chosen alpha threshold, and all the samples we collect from reality, from the real population, we can reject that they are consistent with the null hypothesis. Okay, I hope everybody sees this point clear. But in this case, for instance, here is null hypothesis, here is the reality. Half of the samples we collect from reality, they will be beyond the threshold, as you see, but half the samples we collect, half the sample means will be on the lower side of the threshold, or in the inner side of the threshold, and so we won't be able to reject. So any sample that we collect that has a mean here won't lead to rejection of the null hypothesis. Okay, because this is the rejection area, this blue part, you see. If we collect the sample that has a mean here, we collect dots from the red distribution, it has a mean, it turns up to have a mean here, and we won't reject the null hypothesis. It turns out to have a mean here, then we will reject the null hypothesis. The power is 50%. There's 50-50 chance. Okay. And what else can we see here? Of course, if reality was closer to the null hypothesis, then the chance of failing to reject would be even higher, right? The power would be lower. Even though the null hypothesis is in fact wrong, the null hypothesis says the mean is 0. In reality, mean is true here. Even if the null hypothesis, for instance, is still 1 and the reality has a mean of 1. Sorry, if the null hypothesis has mean 0, reality has a mean of 1. Null hypothesis is wrong, but we might still frequently fail to reject the null hypothesis, as in this case. Can I stop this guy here? No. Well, anyway, you can play with that yourselves. But I hope you've understood what I'm talking about. When collecting samples from this red distribution, which is the reality of the real population, and comparing the sample means with what is described by the null hypothesis in blue, if the sample means are beyond the rejection area, we have high power. We are always able to reject a wrong null hypothesis. But in case where the difference between the null hypothesis and the reality is smaller, then our power will be less, and we might be frequently failing to reject a false null hypothesis. Here, with 48% of the time, we would be failing to reject a false null hypothesis. Again, standard error is also a factor here. If we had larger sample sizes, then the distributions would be narrower and our power would be higher. Okay. This, I guess we already mentioned. Increasing sample size, how does that affect the results of a test? How does it influence type 1 error? How does it influence type 2 error? It does not influence type 1 error, okay? Type 1 error is determined solely by the pre-chosen alpha here. Oops, sorry. Pre-chosen alpha, that's what determines the type 1 error. If we want to reduce type 1 error, choose a lower alpha. If you want to reduce false positives, choose a lower alpha. This is a bit sometimes confusing for people, so think about it and try to understand. But power is directly a factor in, the sample size is a direct factor in shaping type 2 errors. The higher the sample size, the lower the standard error, and the lower will be type 2 error. Okay, this is important. Sample size increases power, decreases type 2 error. It does not influence type 1 error rate. Type 1 error rate is affected by alpha. Okay, so let's study another example. For simplicity, the book has chosen very similar examples. Here we are collecting again flowers that can be of two types. Do you see the difference? One is right-handed, one is left-handed, some kind of chirality that you also have in snails and stuff. And the question here is how this right or left-handedness is inherited. And what the data in this case, which is collected, is involves 27 such flowers produced in the F2. So right and left-handed true breeding plants. So homozygous plants are crossed. F1 are all right-handed. So we can imagine if this is a Mendelian locus with single gene, two alleles, full dominance, then the right-handed allele must be dominant. And then in the F2, we have 6 left-handed and 21 right-handed flowers. And the question is, does this do these ratios fit what we would expect from a Mendelian cross, from a Mendelian F2 ratio? And the expectation would be 1 to 4. Here we have, well, close to 1 to 4, not exactly 1 to 3.5 or something. Sorry, not 1 to 4, 1 to 3. And here we have 1 to 3.5. So in this case, what would be our test statistic? The null hypothesis, the alternative hypothesis, the null distribution, and the p-value. Well, the test statistic would be the proportion of left or right-handed flowers wouldn't matter, right? Or the numbers out of 27. The null hypothesis would be that these numbers out of 27 follow the 1 to 3 ratio. So if it's 27, the expectation would be something like 27 over 4, 7 left-handed flowers and the rest right-handed. It's not an integer. And the alternative hypothesis would be something like the proportion should be anything but 1 in 4. Okay, and the p-value would be, sorry, I hope I didn't confuse you here. So this is 1 to 3 ratio, and this is 1 in 4. It's the same thing, right? 1 to 3 ratio. In total, we have 4 events. 1 of the 4 is being left-handed. We're talking about the same thing. And the p-value here would be any observation, the probability of observing something as extreme or more extreme than what we originally observed. So expectation is 7. What we observed was what, 6 in 27. So observing a ratio less than 6 in 27 or higher than or equal to 8 in 27 or more. Why 8? Where does 8 come from? Well, 6 is as much deviant from 7 as 8 is deviant from 7, right? It's easiest perhaps to see in the graph. Here we have, this is the null distribution. It again describes the probability of observing 0 to, well, here it's cut at 18, but this of course continues up till 27. The probability of observing each of these events out of 27. And here what we have as 8 is 7 plus 7 minus 6, that's 8. So a result as much deviating as extreme on the other side of the expected value. This might be slightly confusing. If so, please, you can ask me to explain during lecture hours as well. But this is the observed data. This is the sum of the probabilities of observing something as extreme as the observed data or more extreme under the null hypothesis, this area, some of this area. And here, this tail is the probability of observing, of course, goes beyond the probability of observing something as extreme on the other side, as extreme as observed or more extreme. On the other side of the expected value of the null hypothesis, that's 7. And where does 7 come from? Again, it's just the null hypothesis just defines the expected proportion as 1 in 4. We have 27 events, 27 in 4. If you think about it a bit, you'll digest. Okay, so if you sum up all these p-values, the p-value you get is 0.8. It's pretty high. It is not surprising at all that it's so high because it covers most of the area. The sum of all this area is 1, right? And the p-value includes all the area except for just this bar, which is, we can already see its frequency less than 20%. So we could already guess that the p-value would be very high by studying the observed value and the null distribution. If I showed you the null distribution and if I gave you potential p-values, if I showed you the null distribution and the observed value, and if I ask you what p-value might be, would best fit the situation, you should be able to guess that it would be high. Okay, so this is obviously higher than than alpha, so we would eventually fail to reject the null hypothesis. By the way, the book calculates the p-value here in a slightly, I think, confusing fashion. They suggest calculating the area here and then multiplying that with 2. But the problem is these two areas are not symmetric. So in the other case we studied here, the distribution is symmetric, right? Distribution is symmetric, and so the tail here and the tail here have the same area. They're equally distant from the expectation and they have the same area. But unfortunately, this distribution, I mean, this part is not symmetric. And yeah, I mean, you can already see that the bars are not of the same size. And therefore, in fact, what the book is suggesting, I mean, it's a rough solution, but it's not a very good solution. It's a quick and dirty solution, as people say. But yeah, what I'm showing you here is better. And anyway, you'll be learning how to solve, calculate these probabilities and how to solve this later. So you can ignore the book solution. And yeah, if you got confused about this, don't worry, we'll eventually, it will be clear also, more clear in the coming weeks. Okay, yeah, in either case, the p-values are pretty high and we fail to reject the null hypothesis. What does failing to reject mean? We have, it means the data is not inconsistent with the null hypothesis, right? There's no reason to suspect the null hypothesis is wrong. It doesn't mean that the null hypothesis is correct, but there's no proof against the null hypothesis. So we might, yeah, we might not find it reasonable to, it might be, with this result with the other results together might lead us to assume that this chirality is in fact transmitted in a Mendelian fashion. It would be support for that. But of course, important thing, failing to reject can also be caused by, it can be caused by the null hypothesis representing a good model, but it could also be a sample size is too small to reject. Perhaps if the effect we were talking about was a slight effect, like the polio vaccine case, think of that case, then you really might need to have, because there's so much background noise, you will probably need a lot of a very large sample size to be able to reject the null hypothesis, to find an effect of 1% or 1 in 1,000 or whatever, which might still be important for you. Yeah, if there's too much noise and if the sample size is small, then you might easily fail to reject a wrong null hypothesis, right? And that we also already saw here. So when the null hypothesis and the real data, real reality are different. So the null hypothesis is wrong, but we fail to reject the null hypothesis. And if we had a smaller sample size, then this would mean the distribution here would be fatter, and this one would also be fatter, and that would mean we would be failing to reject even more frequently. Yeah, and I just also added that these are mutually exclusive, that the data might be noisy, plus the sample size might be small, plus the null hypothesis might be representing a good enough model, perhaps not the exact representation of reality, but close enough representation, and we might be failing to reject. Okay, we're approaching the end, and for that, we should touch upon this issue of two-sided versus one-sided tests, also called one-tailed tests, and p-values calculated from these tests are one-tailed or one-sided p-values. And we can perform a one-sided test whenever there is a good, strong reason a priori before we collect the data to assume that deviation of the alternative hypothesis from the null hypothesis would be in only one direction. So if we can assume that deviations will be happening only one direction, then we can use a one-sided test. The result is that when we're calculating the p-value, we calculate it not from both tails, but only from one tail. The tail where we expect deviations would be happening in the direction of. So there's one example. It's just analogous to the toad-handedness example, again, we have two state outcome, an event with outcome of two states. People are shown the photo of a girl and then the photos of two adult men, and then they're asked which one is the father. And this is repeated 18 times on 18 independent people, and there are 13 correct guesses and 15 wrong guesses. So there are two types of outcome, correct or wrong, right? 18 trials, our sample size is 18. So is this ratio 13 to 5? Is this ratio more than expected by chance? That's our question. It's just like the toad example where we had 14 to 4 right-handed toads. Here we have 13 to 5 correct versus wrong guesses. What would be our test statistic? Our null hypothesis, alternative hypothesis, blah, blah. Test statistic could be just the number of correct guesses out of 18. And the null hypothesis would be, again, the proportion is 50-50, right? If there is no effect, then the father should be correctly or wrongly guessed with equal chance. So proportion would be 50%, and the expected value would be 9 again. The alternative hypothesis, now that's different. The alternative hypothesis would be the proportion being larger than 50%, more correct guesses than expected, and then we can calculate null distribution again using simulation or using the binomial probability, and then finally we can calculate the p-value. Okay, so test statistic, we said proportion correctly guessed cases of a father. Null hypothesis, alternative hypothesis, p larger than 0.05. Previously, our previous case, we had said p, what was that? Sorry, the alternative hypothesis, yes. Here, the null hypothesis was the same. And the alternative hypothesis was described as p not equal to proportion, not equal to 0.05. But here we have, okay, larger than 0.5, not 0.05, 0.5. And the p-value is the probability of observing something as extreme as observed given the null hypothesis, but calculated only from one tail. And this is the same null distribution. Null distribution is the same, but how we use it is different. This is the observed data. Okay, now it's a 13. But we ignore deviations on the other side. We only take into account deviations on this side. So we're calculating the probability of observing something as extreme as 13 or more extreme or larger under the null hypothesis. If everything was random, what's the chance of observing 13 or more extreme? Okay, and that turns out to be, well, nearly 5%, slightly lower than 5%. And well, you might, what do you conclude? Okay, it's lower than 5%. You might say, okay, you reject the null hypothesis, but in fact, there's a good, given this all the setup, it also means there's a 1 in 20 chance that this result could have happened just by chance, right? So it does call for more data collection. I guess everybody would agree with that. But it also hints that there might be something going on. So with more data collection, it might be worthwhile collecting more data, but we shouldn't put like too much effort and perhaps collect another cautious set of data. If those also support us in the same direction, then we might go out and perform a large experiment, for instance. But yeah, we have to be cautious. Yeah, something that is important here is that if we had performed a two-sided test, as you see, it would have involved calculating the p-value from both tails, as in here, and the p-value would be something like 10%, close to 10%. And we would not have called that significant. Yeah, so in general, one-sided p-values, if the null distribution is symmetric, one-sided p-values are half the p-values of two-sided tests. And so it's easier to reject the null hypothesis using one-sided p-values. In that sense, one-sided tests can be more powerful. Type 2 error less likely. But our book also correctly emphasizes that if there is no strong evidence in advance that the alternative hypothesis would be in one direction, that deviations between the null hypothesis and reality would be happening in one direction, then it's better to stick to the two-sided test. In this case, it probably did make sense because if there's resemblance, if there's genetic relationship, that should come with higher similarity than expected, right? I mean, that would make sense as much as we know genetics. So here running a one-sided test does make sense, but for the toad example, for instance, there wouldn't really be reason to expect that toads might be right-handed over left-handed, and they're running a one-sided test would probably not make sense unless there is evidence that I don't know, hundreds or thousands of other animal species have been shown to be right-handed, but much less frequently left-handed. Unless there's such evidence, there's such background reason, one should do a one-sided test. One should do a two-sided test, I'm sorry. And the book also, again, very rightly emphasizes that it would be wrong to first check the data, observe how the data might be deviating from random expectation, and then choose a one-sided test depending on the observed deviation. That would be like cheating. This is important, if you don't really have a good reason to expect left-handed or right-handed toads to be more frequent, if you first collect the data and then you say, I run a one-sided test, this is not good. If you didn't have a reason in advance, then you should run a two-sided test. And also, this is also critical all throughout your later research life. Please state whether once you do a test, state whether it's a one-sided or two-sided test for other researchers to be able to interpret your results in the best way. Yeah, so I here have an example, a counter example of how research should be done. For instance, let's say you're asking, would first-year university students differ in weight than fourth-year students? And well, you could come up with reasons to argue that first-year students might be heavier because, university exam is very stressful and they've been eating a lot at home. Or you could also argue fourth-year students are heavier because they've been studying like crazy. Who knows? I mean, both could be valid. We don't know. And what you shouldn't, if you want to test this idea, once you collect data, what you shouldn't be doing is if looking at the data, finding which year has different mean. I mean, which year is lighter, which year is heavier, and then running a one-sided test. this is not good practice. Okay, you should, there's no obvious reason for one or the other to be valid, then run a two-sided test. This is wrong. Okay, one before last, yeah, if we collect data and compare with the null hypothesis and calculate a p-value, in general, if the p-value is larger than 0.05, then the confidence interval we can construct based on this data, based on the sample, should also include the null hypothesis. Okay, so this is referring to the previous week's discussion, where we saw how we can construct a 95% confidence interval for the population mean. The population mean here would be the null hypothesis, and if the sample, so for instance, in the toad example, from the sample we would the proportion we observed in the sample was something like 0.8, and the 95% confidence interval might extend from 0.6 to if it's symmetric, it would be close, something like 1, right? And then this is the 95% interval, and if the null hypothesis is outside the 95% interval, this means the p-value is also larger than 0.05. So this 0.5, so the proportion of false positives we accept also corresponds to, when we construct the confidence interval, it corresponds to the proportion of events where we would be tolerating false results, false positives. And just the opposite, so if the I'm sorry, by the way, oops, I would be describing this second situation here. Sorry about the confusion, not this one. So if the p-value is less than 0.05, then the confidence interval should not include the null hypothesis, okay, like this situation. But if the confidence interval includes the null hypothesis, then the p-value is larger than 0.05, like in the case of the right and left-handed flowers. So there the proportion was something like 1 in 3, 1 in 4, something like, let's say 0.2, and the expected value was, let's say, 0.25, and sorry, 25, and the null hypothesis would be, sorry, the confidence interval would be, let's say, extended from 0.1 to 0.3. Okay, this would be the confidence interval describing the expected values of the where the population mean might lie. And if the null hypothesis lies within that range where the population mean could lie, that means we cannot reject the null hypothesis, fail to reject, okay, fail. Whereas here, this is the 95% confidence interval for the population mean based on the sample again, but the null hypothesis is outside this range. So here we reject. Okay. they're basically telling us the same story. In one case, they're telling us the sample is inconsistent with the null hypothesis. Here, they're telling us the sample is consistent with the null hypothesis. And in general, these results would be consistent if we're constructing them using similar methods. What those methods will be, we'll be talking about in the coming weeks. Okay, so please solve all the questions without solving questions at the back of the book. It will not be possible to really digest the content. And again, I will tell you 100 more times through this course that whatever you learn here you will be using throughout the rest of your research life. So please try to spend as much time as possible, discuss with your friends, and so on. And yeah, also read this chapter, which gives a nice background on what the meaning of statistical significance is versus biological importance. Okay.